Okay, so we're starting chapter 4 of the conformal field theory. And what we want to do in this chapter is to start exploring some of the consequences of what it means to have conformal symmetry. I'm going to start off a little bit more generally, and the basic idea I want to start off by exploring is embodied in a theorem called Noether's theorem. What Noether's theorem tells us is that if you have a continuous global symmetry, you get a conservation law. So symmetries imply conservation laws. To make the discussion transparent, we're going to start off discussing what a symmetry is. Then we're going to discuss what types of symmetries you might have. And then we'll talk about Noether's theorem. We'll prove it, and we'll see what conservation laws we get from conformal symmetry. So that's the plan. Let's get going. So if I was to ask you, what do you mean by a symmetry? Well, you might give an answer like this. Let's imagine that we have some disk. So I've drawn it here. And my picture is not perfect, but I want you to imagine that this is a perfectly round disk. It's absolutely perfect. I'm going to ask you to close your eyes, and while your eyes are closed, I'll rotate this disk. And imagine that I rotate the disk through some angle, theta. Okay? Then I tell you to open your eyes. If when you open your eyes, I tell you, can you tell how far the disk was measured? And in answering this question, you're allowed to perform any experiment you like, to examine the disk in any way that you like. You're free to do anything. If you cannot tell in any way what theta is, then that means you cannot tell that I've rotated it. And then we would say that rotations are a symmetry of the disk. So this is one notion of symmetry, and I think this is often how people put the idea of symmetry across. This is a symmetry of an object. Well, sometimes in a theory, we might look at a state and we might want to know what symmetries a given state has, and we might calculate the implication of those symmetries of the state. But this is not what we're after here. This is not the notion of symmetry that we're interested in. What we're interested in here is a symmetry of the laws of physics themselves. So let me give you an example of what I mean. The laws of physics today are the same as they were yesterday, and the laws of physics will be the same tomorrow. So one of the things that we firmly believe and have checked is that the laws of physics don't change with the passage of time. To say that in a slightly more fancy way, we say the laws of physics are time translation invariant. Now, the nice thing about the example of the disk that we just discussed is that we gave a definition of symmetry that you could actually check with an experiment. You could do some experiment and then tell if there was a symmetry of rotations for the disk. Now I want to know, could I perform an experiment that would test whether I've got a time translation invariance of the laws of physics? And of course, there is a simple experiment, or there's a simple way to phrase this. I could do the following. Imagine I've got a tennis ball. I'll take that tennis ball, throw it towards the wall, and watch it bounce off the wall. Let's imagine I film the whole process. So as I throw the ball, it moves along some arced path because of gravity. It hits the wall, it rebounds from the wall, and continues to travel. If I show you the film that I've recorded and I say to you, is it possible to tell when I made this film? Well, you could analyze the film. You could analyze the ball's trajectory and so on. What would you be doing? So you need an accurate description of the gravitational field of the Earth. Then you would know what was the force acting on the ball, and you could calculate the trajectory that the ball followed. You could then compare it to the film and verify that this is indeed the correct trajectory. But having done that, you have no idea when the film was filmed. And that's because Newton's laws remain the same. if I filmed the ball hitting the wall today or 10 years ago, you would never be able to tell the difference between those two cases. So this is one experiment that we could do. Film some physical phenomena. If we cannot tell when the film was made, then the laws of physics are time translation invariant. And for every law of physics, we should be able to make a statement of that type. Let's think about Lorentz invariance, okay? So the group of rotations and boosts. And we expect that the laws of physics are invariant under those transformations. So let's take a look specifically at boosts. Imagine I've got a bunch of charged particles that are interacting. I can study their dynamics. I can verify that these charged particles are correctly described by Maxwell's equations. I could work out some charge densities and current densities to describe where the particles are, work out the electric and magnetic fields, calculate the forces on the particles, and work out their dynamics perfectly. So I find, if I'm at rest, that my charges obey Maxwell's equations. Now imagine that you're moving in a frame boosted with respect to mine. Actually, you're on a train moving with some velocity. On that train, you are studying a set of charged particles, and you can verify that your charged particles also obey Maxwell's equations. As long as the train moves with a constant velocity, you will observe Maxwell's equations, and it doesn't matter what the velocity of the train is. So by just studying the charged particles, you could never tell if the train is at rest or it's moving with some constant velocity. And that implies there's a symmetry of nature. If you boost to some other inertial frame, all the laws of physics remain unchanged. All of the predictions are exactly the same. Okay, good. Actually, now that we're here, let me just make a comment. This is something that confused me as a graduate student. You know, often when people want to define an inertial frame, they'll say it's a frame that's not accelerating. Well, as a grad student, that didn't really make sense to me. And the thing that was tough is, what does it mean to say a frame is not accelerating? You know, it was hard to make clear, simple sense of what not accelerating means. What I found was a much more helpful way to think is that you can define an inertial frame to be a frame in which the physics of charged particles is described perfectly by Maxwell's equations. That's something very easy to check. You just take a bunch of charges, study their trajectory, study their dynamics, solve for the dynamics using Maxwell's equations. Do Maxwell's equations predict the dynamics that you've observed for the charges? If yes, then you're in an inertial frame, and if no, you're not in an inertial frame. To me, that just seemed like a much clearer definition. Okay, so now we've talked about what a symmetry is and how you could detect it by doing some simple experimental investigation. So I hope you agree with me that we've got some idea of what it means to have a symmetry. Now let's go a little bit further, and we want to come up with some sort of a mathematical characterization of a symmetry that we can actually use to do something. And we're going to stick to Lorentz invariance to motivate our mathematical characterization. So imagine I'm in my lab, I have my charged particles. As before, I'm studying their dynamics. I write down some electric fields, some magnetic fields to describe the positions of the charged particles and how fast they're going. I'll write down some current densities and some charge densities. And at the end of the day, I know if I take this collection of electric currents and magnetic fields and current densities and charge densities and I plug them into Maxwell's equations will be obeyed. You are in some different frame. You're studying the same collection of charges, the same collection of currents. Because you're moving at a constant velocity with respect to me, you're also in an inertial frame. And you will also see that Maxwell's equations hold. So your electric fields, your magnetic fields, your charge densities, your current densities are a solution to Maxwell's equations. Now, yeah, I can easily figure out how to get your solutions. I'll just take my solutions and perform a Lorentz transformation. And the result of that Lorentz transformation gives me your solutions. That's a really important idea. If we perform a Lorentz transformation, a symmetry transformation, we'll map my solutions to the equations of motion into your solutions to the equations of motion. So that's our first mathematical definition of a symmetry. A symmetry maps solutions to the equations of motion into solutions to the equations of motion. Great. So now we're going to go a little bit further. We'll continue in a minute.